Lecture 36 is the second lecture on optical properties of materials. In this lecture, we talk about anti-reflection coating and dielectric mirrors. We then talk about the reflection of metal using the classical Drew model to explain it. And then we talk about the phonon absorption and the result of infrared absorption spectroscopy. Finally, we talk about Rayleigh scattering and light attenuation in optical fibers. So first, students should be able to describe the working principles of anti-reflection coating and dielectric mirrors. For anti-reflection coating, in its simplest form, could just be a single transparent layer with appropriate index reflection and thickness. The function is to reduce the overall reflection of a particular material. So for this anti-reflection coating, when light is reflected off the front and back surface of this anti-reflection coating, these two partial waves, if they can interfere destructively, then we can possibly reduce the reflection. So to have a destructive interference, we need the phase angle difference between A and B partial waves to be 180 degrees or more, or 540 degrees, pi, 3 pi, and so on. So that requires the thickness of this material to be a quarter wavelength multiplied by an odd integer, a quarter, 3/4, and so on. And obviously, it's related to the wavelength inside this material. So we also need to know the index reflection for this material. Additionally, to allow these two partial waves to cancel completely, the index reflection will also have to satisfy this requirement, being the geometric average of the index reflection of the two materials on either side of this AR coating. On the other hand, if we can allow these partial waves to interfere constructively, then we may possibly enhance the reflection, so that could be used to make a so-called dielectric mirror. So in this case, when we have these multi-layer stack, each of those layers have quarter wavelength thickness, then the additional light path in these material will be 180 degrees. However, considering that the light reflection of 1,2 interface versus 2,1 interface will have a reflection coefficient 180 degree off, there's a sign change that will give you additional pi phase shift that give you overall 2 pi phase shift for all those partial waves that allows the waves to constructively interfere, that give you almost unity reflectance in this situation. The second student outcome is to explain why metals are highly reflective using the classical Drew model. So based on the classical model, we can obtain the dielectric behavior, the dielectric constant as a function of frequency for these metals. In this case, 1 minus omega p squared over omega squared. This omega p is so-called plasma frequency, which is related to the concentration of the free carriers in metals. And so if you plot out this function, the dielectric constant as a frequency, then you'll see that for angular frequencies below the plasma frequency, the dielectric constant will be a negative value. So if we then take the square root to obtain the index reflection, then we'll see that the index reflection will be a purely imaginary number. That is, the n will be 0 and then kappa will be some positive values. So if you plug that into reflectance equation, that will get you 100% reflectivity. So that's why metals are shiny and reflective. But obviously for actual materials, then they have finite conductivity, then the reflectance will deviate from 100% reflectivity. So the next student outcome is to describe the processes involved in lattice absorption and Rayleigh scattering. For lattice absorption, it's basically absorption of a photon to generate a phonon inside materials, and this because the phonon energy is typically on the order of a few milli-electron volts to maybe hundreds of milli-EVs. That means the corresponding wavelength of the light, the photons will be in the infrared range, so that's why we call it infrared absorption as well. So this shows you that for materials like gallium arsenide or cadmium ternite, you see these peaks happening in the infrared range, which is on the order of, in this case, 30 to 60, 70 micrometers. Remember the absorption coefficient, the extinction coefficient kappa is related to the imaginary part of the dielectric constant. That means these materials are absorbing light at these wavelengths. And so the requirement is that the phonon energy is the same as the photon energy. That requires the wavelength of the light to be in the infrared spectrum. And obviously, in addition to these lattice phonons, we may also have localized phonons due to impurities. So by looking at the absorption coefficient or the extinction coefficient corresponding to these modes, we can determine how abundant those defects are. That is infrared spectroscopy. On the other hand, for dielectrical particles that have sizes smaller than the wavelength, we may also have the so-called Rayleigh scattering behavior. That is basically these dielectric particles will be polarized because of the incident electromagnetic field, and the dipole induced in these dielectric particles will then emit radiate energy to the environment again. So in this case, the frequency response is that the frequency of the emitted light is actually the same as incident light. So that means the photon energy is the same. So we have the so-called elastic scattering. But obviously, the direction of the emitted photons are going everywhere, that resulting in a loss of the through wave intensity. So for the attenuation coefficient, for the Rayleigh scattering, it typically increases as the wavelength is reduced. And then obviously, if the index reflection contrast with the environment is bigger, that will also give you bigger Rayleigh scattering. So finally, you should be able to explain how optical fibers can allow propagation of optical signals over long distance. There are two requirements to allow light wave to propagate for long distance in optical fibers. One is that the fiber has to be extremely transparent. And the second is that light wave has to be confined in the optical fiber. So let's look at the confinement effect first. For a typical optical fiber, we have a core material, which is glass, whose index refraction is slightly higher than the index refraction for cladding by a 1.5% difference. But that 1.5% difference is sufficient to allow total internal refraction to occur for angles greater than, let's say, 81 degrees. So for these light, we will have total internal refraction at the core cladding interface that allows the wave to be completely confined in the optical fiber. On the other hand, the fibers are extremely transparent. You see lattice absorption limiting the absorption in wavelength greater than 1.5 micron. For wavelength less than that, we have the Rayleigh scattering behavior. Remember, the Rayleigh scattering is more significant for shorter wavelength light. That's why the sky is blue on a hot, sunny day. So for longer wavelength, you see this Rayleigh scattering tail. And then we have these impurities often existing in a glass, like hydroxyl groups. They will give you certain absorption peaks. So that leaves you a window right at about 1.55 micrometer that give you lowest attenuation. This attenuation is defined as 10 dB times the log 10 of the intensity reduction. So if the intensity is reduced by 10 times, that corresponds to an attenuation of the light wave by 10 dB. And obviously the attenuation scales with propagation length. So for 50 kilometers, you're going to have about 10 dB, then get you 10 times reduction. So 10% of the energy will be able to go through 50 kilometers long distance. That is pretty long, but obviously we'll have to have amplification stages to allow the light wave to be propagated to, let's say, Europe, China, and other long distances. This is the end of the review for this lecture.